Hi there, folks. Today we're going to be covering section 1.4, 1.5, and 1.6. To begin with, we actually have this conceptual problem, and we're going to see a lot of these bigger picture conceptual questions as we're going through the course. This one's actually leading to ideas that we're going to be seeing in chapter 2. And it's the question of what is 2 to the pi? Now, when you think about 2 to the pi, it's definitely something we can just plug into our calculator, and our calculator can handle it. Let's see if I can get my calculator on the screen real quick. And if we do 2 to the pi, I end up getting 8.824977827. But the question is, what does 2 to the pi actually represent? And that's something a little bit harder to conceptualize. And so we know a fair amount about exponents and how they work, right? We know that if we have a to the 1 over n, that's the same as taking a radical. If it were a to the m over n, well, it's the same as taking a radical with a base of n, but then the exponent on that a is the numerator, the m value. And we could also do it this way if we had the denominator was, let's see, yeah, if m was a negative number or something, then we could get something like this to pop out of it. But that's not something that is going to help us in this case. 2 to the pi, well, pi is an irrational number. What do you do when you have an irrational number? We're no longer able to do this 1 over n. In this case, the n needed to be a natural number, or the m and the n both needed to be natural numbers. We can handle fractional exponents, but we don't have the tools needed to do irrational exponents. So how do we do it? And that's what chapter 2 is about. Chapter 2 leads to these ideas of limits, the idea of what if we approximated it in an infinite way? And the way we would actually break it down is we could start with the idea of what is 2 to the 3. And well, 2 to the 3, we know that's 8. Well, what's 2 to the 3.1? Well, that is a rational number, so we should be able to figure that out. Same with 2 to the 3.141 or 2 to the 3.14159. The further out we go, the closer we're going to get to an approximation for 2 to the pi. And if we did this infinitely, if we just let this sequence go on indefinitely, eventually we would get something arbitrarily close to what the solution for 2 to the pi is. And that's how we would calculate something like this, where we have a number with an exponent which is an irrational number. This is kind of a new way of thinking because we don't really have a way of getting the exact answer for 2 to the pi. 2 to the pi is the exact answer. But what we can do is we can get arbitrarily close to that value using what's called limits. Today, we're not going to be focusing on limits. That's what next time's about. Today, what we're going to be doing is we're going to be finishing up all of the Algebra 2 material, which you're supposed to have for this course. And so again, we'll be skipping around a little bit because you should already know all this stuff. But today we're going to be talking about exponentials, logarithms, and sequences and difference equations. Shouldn't be too bad. Should be a little bit quicker than last time. And so let's jump into it. And let's start with just some random problems that we can do with exponential functions. Again, I don't know that we want to do all of them, but let's do a couple of these at least, maybe these first 3. And so I will write these first 3 down, and then we will work through them as a group. Or if you want, you can even pause the video and try them on your own. So 14x squared y to the negative 6 over 21x to the negative 17 y to the negative 2 all to the negative 2. Let's try that one first. And so with this one, we have a lot of different things going on. And so it's 14x squared y to the negative 6 over 21x to the negative 17 y to the negative 2 all to the negative 2. Somehow we've got to reduce this thing. And we can start on the inside, or we could try and deal with the outside first. But honestly, going from the inside out is probably the better way to approach this one. And so let's start just by cleaning the 14 and 21. We know that 14 and 21 both have a factor of 7 in them. And so we can cancel out the 7s, leaving us with a 2 over 3. Now, if you remember with negative exponents, whenever you have a negative exponent, you can actually move it to the other side of the rational expression. And so the x squared could stay on top, but then the x to the negative 17, we could bring from the bottom to the top. With the y's, both of them are negative, and so we could flip-flop both of them, giving us a y squared on top and a y to the 6th on the bottom. And now if you want, you can combine and cancel these. And so the 2/3 will hang out. X squared times x to the 17th, we add our exponents, giving us x to the 19th. On the bottom, we have a y squared and a y to the 6th. Since we have more on the bottom, we can subtract in order to figure out the number of y's we have. And so we'll have y to the 4th, and it will be on the bottom. We then still have this negative 2. Now, with the negative 2, we have two things. One is it's a negative, and the other is that it's all squared. For the negative, remember that means that we can flip everything. And so if we flip everything, we'll get 3y to the 4th over 2x to the 19th. And now it'll all be to the positive 2. And our last step will be to square everything. The 3/2 we can square to give 9/4. Y to the 4th squared gives us y to the 8th. Because remember, we're just doubling the exponent in that case. And same with the x to the 19th, that will become x to the 38th. And that's our solution. Double check everything, make sure it all makes sense, because this is the type of problem which we're probably not going to see much this semester, but it's going to be in the background of a lot of the problems we do. Most of the stuff we're going to do is focusing on functions. And sometimes when you're dealing with functions, you need to simplify something before you can actually play with it. And so this is how you would simplify something like that. For our next example, looks like we're going to be rationalizing a denominator. And so number 2 is the square root of x over the square root of x minus the square root of y. Now, the issue with this one is we're not supposed to have radicals in our denominator. Since we're in calculus, we're going to see lots of radicals in our denominators, and we're going to be okay with it. But from a pre-calculus perspective, this is something which we would consider not simplified. The strategy we would use to simplify it is to multiply by the conjugate. And so the conjugate, remember, is going to be the exact same expression you have in the denominator, just with the sign changed. And so we're going to multiply the top and bottom of this by square root of x plus square root of y. When we do that, on the top, it's not going to become that nice. Square root of x times square root of x is x. And then square root of x times square root of y gives us square root of xy. On the bottom, square root of x times square root of x gives us an x. Square root of y times square root of y gives us a minus y. And then the cross terms cancel out. So square root of x times square root of y minus square root of x square root of y. And so this then is our answer. Now the question becomes, is this a nicer format than our starting format? And well, honestly, I kind of liked our starting format. And for most calculus things, the starting format would be what you might keep it at. But the idea of being able to use the conjugate is going to be very valuable. Once we get to chapter 2, we'll actually be using the conjugate to move things from the top to the bottom, as well as from the bottom to the top. And so make sure you feel comfortable with that technique of using the conjugate. We'll do number 3 as well. Number 4 we'll probably skip, but number 3 is worthwhile. Because remember, when we're talking about radicals and exponents, well, radicals are just fractional exponents. And so when we see something like x to the 1/6 times x to the negative 2/3 over x to the negative 3/2, well, it's not technically simplified until we've eliminated all of the rational exponents. And so we'd want to write this in terms of radicals, ideally. The challenge with this one is we have all of these fractions, and the question becomes, what is the best way to deal with them? We could turn it all into radicals in the first step, but instead what I would probably do is I would probably bring everything to the numerator. Because remember, when you're multiplying things like this, really you're just adding or subtracting your exponents. And so if we moved everything to the top, we would get x to the 1/6 times x to the negative 2/3 times x to the positive 3/2. Because when we move this to the numerator, it changes sign. Now we can just add these exponents. And if you want, you can get a common denominator and go that approach. I'm feeling lame today, and so I am going to use my calculator, because one of the benefits of the TI 30X is it does fractions very, very well. And so I can do 1/6 minus 2/3 plus 3/2, and I actually get 1 out of it. That's kind of fun. And so in the end, we're not even going to be writing this in terms of radicals, it seems, because this is just a very ugly way of writing x. Definitely double check those numbers, but that does look about right. And so that's kind of a fun one. So these are exponential properties, which in theory you all learned in Algebra 2. Some of them you should have learned even before that. I believe number 3 is something that you do in pre-algebra. And so all of these are things which have been seen before. If you don't feel comfortable with them, I would recommend going and reviewing. And you could just do a quick YouTube search on properties of exponents, and you'll be able to get the laundry list of all of the properties that exponents have. And you can even find some practice problems. Yeah, there's a number of good folks on YouTube that can help out with that. You can also hit up our tutoring center, and so don't forget that. The next thing is to graph. And so graph each of the following. Let's do this first one by hand, because it's good to get practice graphing things by hand. And so if you don't have paper out yet, what are you doing? But see if you can actually graph 2 to the x by hand. And if you want, you can actually create a simple little t-chart. I'll show you how to do that. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So we're going to graph the equation y equals 2 to the x. Now, when in doubt, if you're able to, you can always go back, just create a chart with x and y, and then just plug some values in. Let's say we start at -2, then -1, 0, 1, 2, 3. That should get us pretty far. And so when we plug those values in, -2, we get 2 to the -2, which is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Each one of these corresponds to a point on the graph. And so at -2, we're getting 1/4, then 1/2, then 1, 2, 4. 1, 2, 3, 4. Counting's the hardest part, I swear. And there we go. And that's the curve of y equals 2 to the x. This one is probably the base example that you want to have in the back of your mind when you're thinking about exponentials. Exponentials, as you go to the left, they always approach 0. They never hit 0, but they get arbitrarily close to it. And as you go off to the right, this grows faster than any polynomial out there. And so while it might look quadratic, this is actually much, much faster than a quadratic. And to see what I mean by that, let's actually pull up our good friend Desmos. And so in Desmos, if we graph y equals 2 to the x, this is what the curve looks like. And you can see that it starts by going very close to 0, and then it goes off to infinity very quickly. If we were to compare this to y equals x squared, well, it starts out looking pretty similar, right? But let's change the axis. And so let's change this so that we are letting our y get arbitrarily large. Let's say that our y is going to be going to 10, 100, 1000, and as big as we want. Notice that by the time we hit 15, our 2 to the x function is already around, what is that? 31,000, 32,000. And so it's gotten massive by comparison. Our x squared at 15, I could probably just do the math and get the 225 out of it. And so the exponential, it's leaving that quadratic in the dust. And exponentials do that compared to any polynomial. We can make this the x to the 10th. And it might look like the x to the 10th goes much, much faster, but that's only in the short term. And so if we let this keep on going, and let's go back to our settings and add another 0 or 2. Oop, might have to go a little bit further out. There we go. Because we can see that for the first two numbers, we're going to get that the x to the 10th is higher. But as soon as we let that y value get big, and I mean big, big, the 2 to the x overtakes it. And it'll overtake it every time. And so at this value, let's say up here, we're right around 70. At 70, we're going to be at 8 times 10 to the 20th. With our x to the 10th at 70, we were only at 10 to the 18th. And so this is already 100 times as large. Exponentials get big fast. And that's the big takeaway there. Oop, let's go home. There we go. Now, 2 to the x is one of the important ones. The other one, which is perhaps more important, is e to the x. And we are going to be doing a lot of stuff with e to the x this semester. What's important is knowing e for one thing. So let's make sure that we all know what e is. E is this number, and there's actually a lot of ways to define it. But it's good to actually know what the approximation is for e. E is roughly 2.7182818459045. And that's about how far I know that number. There's a nice little limerick to remember this one. You see, there's two things you need to know about Andrew Jackson. He was our 7th president, and he started office in 1828. That's right, 1828. And on a completely unrelated note, the angles of an isosceles right triangle are 45, 90, 45. How that relates? Well, there are two things you need to know about Andrew Jackson. He was our 7th president, and he started office in 1828. That's right, 1828. And on a completely unrelated note, the angles of an isosceles right triangle are 45, 90, 45. And that's a quick way to remember E out to 15 spots. And so often you'll only need the 2.7, but it's really easy to get all of these other ones. And so for me, I usually just try and go out as far as I can. There's also an E button on your calculator, and so there's no excuses for not just using that. But the bigger question is, why do we care about E? And I'm not sure if I talk about that yet in here, but we can talk about that now. I'm looking at the lecture notes by the by. I didn't do the share screen right there. Here we go. And so when we talk about E, what E is all about is exponential growth and decay. And it turns out, if you remember last time we were talking about rates of change, well, e to the x is one of the only functions which is its own rate of change. And that is huge. That makes it so that it is a very, very powerful function. If you want to find the slope at any point on the function e to the x, well, the slope at that point is e to the x. And that's very, very unique. Again, very few functions actually have that property. And that makes it so that it is the default solution for most exponential models. And when we start thinking about the different types of models we're going to be seeing throughout this course, there's going to be a lot of them where things are growing in an exponential fashion. And again, we'll see why that is later. Really, once we get to chapter 3, we'll start to explore the whys behind all of this. Up until then, it's mostly going to be the hows. And so we're going to be saying, well, do we remember all these functions and can we actually compute some stuff? Once we get to chapter 3, we'll be able to look at the big picture and say, all right, here is how all of this is connected. And we'll show how all of algebra and trigonometry are connected to one another, and how everything in engineering and biology and medicine is all connected to one another. We're not doing that today, though. So for now, just remember that our E number is very valuable for exponential growth. And we can graph it. That's the graph of e to the x. If we were to do a 0.2 to the x, well, that's actually going to flip the graph, I believe. And so any value above 1 is going to have our standard shape. But as soon as we make it so that this is a 0.2, it's going to flip it. And a question might be, why is that? Well, the reason is that this is the same as 1/5. Oh, as I'm getting everything in the wrong place, to the x. But 1/5 to the x is the same as 5 to the negative x. And so all three of these functions are the exact same. But notice that this 5 to the negative x is really just going to be the same as the 5 to the x, but with the flip across the y-axis. And so when we were talking about all of the ways that you can manipulate the graphs of a function, this is a horizontal flip to get this. And that's why the 0.2 to the x is going to be going in the opposite direction. Basically, instead of exponential growth, this is going to have exponential decay, in which this is going to be going down to 0 as quickly as you can get. It will never actually hit 0. And while you see 0 in this, the 6.78 comma 0, that's really just because that's as close an approximation as Desmos can get. If we try to zoom in as close as we want here, eventually we'll see that there is a difference between them. But boy, do we have to get close. And so you can see here that it's a very, very small difference. And so Desmos isn't able to compute that when you're in that zoomed out mode, because it's only going to approximate it to a few decimal spots. But it is going to always be just slightly greater than 0. Our next one, e to the x minus 4 plus or minus 5, this is just going to be a manipulation of that e to the x function. And so if we think of our e to the x function, which we should know the graph of, y equals e to the x. Well, if we did an e to the x minus 4, e to the x Ooh, and can I do it up here? No, it's going to make me do parentheses. There we go. -4 is going to shift the graph 4 units to the right, because that's how it works. We did a -5, it shifts the graph down 5 units. And we could do this by any amount that we wanted. If we want, we could say, make that A, make this a plus B. And then we can shift this graph to the left and right however we want. We can shift the graph up and down however we want. And so e to the x is just the base function, and then we can manipulate it however we want. The next example is an e to the absolute value of x. And this one's going to be a little bit more interesting. Because if we think about this, we know the graph of the absolute value of x looks like this. And so what happens when we do a composition of e to the x with the absolute value of x? Well, it turns out what that's going to do is that's just going to reflect this quadrant 1 bit into quadrant 2. And so our graph will look like this: e to the absolute value of x. And so notice it's just taking the quadrant 1 bit of e to the x, and then it's reflecting it. Down here, it's no longer going to be smooth. It's going to be coming down to a point. It's a point that is even looking like it's at 45 degrees, which makes sense from a calculus perspective. But it raises the question of what happens when we start doing compositions of other functions. For instance, what if we did, instead of an e to the x, we did an e to the sine of x? Well, if we think of what sine of x does, sine of x bounces back and forth between -1 and +1. And so if we think of what this exponential graph looks like between -1 and +1, we should start to see that behavior repeated over and over and over again. So y equals e to the sine of x. It's really just taking our -1 to +1 interval and repeating it at every 2 pi units or so. And so it's a nice way to take a function and make it periodic. What if instead of e to the sine of x, we did sine of e to the x? Well, again, you could ask what that's going to look like. And if we were to do a sine of e to the x, well, e to the x, we know is going extremely slow back here, and then it goes extremely fast to the right of that. And so it should take our sine wave and start out extremely slow and then get extremely fast. So y equals sine of e to the x. And so again, these are things which we want to start thinking about. We want to start thinking about what happens when you take the compositions of these types of functions. Because you're going to get interesting behavior, and the question becomes, what does that behavior look like, and why does it look that way? And so definitely start playing with it. There's only a handful of functions to play with, and so maybe start seeing if you can make those connections. 6, that's a repeat. We don't have to worry about 6. The next says, find the domain of each of the following. And let's see if we can figure these out, or at least some of them. Let's start with the first one. Sine of e to the -x plus 1. So g of x equals sine of e to the -x plus 1. And it's asking us for the domain of this. Well, with this problem, what we want to ask is we want to ask, where can things go wrong? And that's often the way that I think of domain problems. When does the function go wrong? And in this case, we could plug in any number that we want into this section. Because if you plug in anything from -infinity to +infinity, e to the -x is going to give you a number. And so that works fine. And then we can take the sign of any of those numbers. And so that's also not an issue. And so there's absolutely no place where this function is undefined. And so in this case, the domain is going to be all real numbers, everything from negative infinity to positive infinity. It's always nice when you get easy ones like that. The next one's a little bit more complicated. And so the next one is h of x equals square root of 2 minus 2 to the x. And so again, the question becomes, when do things go bad if we're trying to find the domain? And in this case, we have a square root. And so as soon as we see that we have a square root, we know that we can only take the square root of positive numbers, or 0. Anything less than 0 is going to be undefined. And so that means that this bit here, 2 minus 2 to the x, has to be greater than or equal to 0. And now we have a problem we can solve. Looking at this, we could say that 2 has to be greater than or equal to 2 to the x, or if you prefer, 2 to the x has to be less than or equal to 2. And 2 to the x is equal to 2 when x is equal to 1. So that tells us that x has to be less than or equal to 1. And sure enough, you could try some numbers. If you wanted to plug some numbers in here, if you said x is equal to 0, we're going to get 2 minus 2 to the 0, which is 1. So that gives you square root of 1, no problem. If you plug in x equals negative 20, well, 2 to the negative 20 is going to be a tiny fraction. 2 minus that, no problem. If you plug in 5, well, 2 minus 2 to the 5th is going to be negative 30. We can't take the square root of negative 30. And so x being less than or equal to negative 1 is going to be the correct domain. So in this case, the domain, written in interval notation, would be everything from negative infinity all of the way up to 1, and including 1. Cool. Next one, again, it's a little weird. And so for this one, it is f of x is equal to the square root of e to the x over e to the sine of x. And so what is the domain of this function going to be? As with all of these, feel free to pause and answer the question before we go into it. But for this one, again, we're going to ask the question, when do things go wrong? And looking at the numerator, we have a square root, and we know that we're only allowed to take the square root of a positive number. And that's not a problem here because e to the x is always going to be a positive number. And so no issues there. With this one, e to the sine of x, well, e to the sine of x is in the denominator. And so that means that we can't have 0 in the denominator. While sine of x will give us 0, e to the sine of x will never be 0 because e to the anything is always greater than 0. And so we have no issues here either. Because of that, the domain is again going to be negative infinity to positive infinity. Here's a question for you. What does the graph of this function look like? Well, you should pull up Desmos and take a look at it. The last one is perhaps the most complicated one. And it is f of x equals x plus 1 over 1 minus e to the sine of pi x. And so again, we want to be asking questions, when does this go wrong? Our numerator, we have no issues. Our denominator, we have some issues because this denominator is actually going to equal 0 sometimes. And so we could ask the question, when is 1 minus e to the sine of pi x going to be equal to 0? Well, that would mean that e to the sine pi x is equal to 1. Well, e to the 0 is equal to 1. So this tells us that sine of pi x would have to be equal to 0. And sine is going to be 0 an infinite number of times. Because it's sine of pi x, it's actually going to be mostly all of the integers, because we know that sine of x is going to hit 0 every pi units. But because this is going at the speed of pi, whenever x is equal to -2 or -1 or 0 or 1 or 2 or any integer value, we're going to get that this is equal to 0. And so the domain in this case is not going to be something we can write in interval notation, but we could say that this is the set of all x which are real such that x is not an integer. This is called set builder notation. Basically, this is a description of the types of numbers we're going to be seeing, and then this is any restrictions that we have on it. And so this is x is any real number where the real number symbol is given by a capital R, such that x is not an element of the integers. The integer symbol being this, which corresponds to all of these numbers. And so that one's a little bit more complicated. Certainly writing it out is much more complicated because you're not even able to write it out in interval notation. But really you want to be able to understand what the domain of this function actually is. You want to know when things go bad with these functions, because so much of what we're going to be doing is we're going to be exploring horrible looking functions and asking what they look like and how they act. Let's share the screen and continue with our lesson. So the next big topic is the inverse of a function. And so inverses of relations and functions. The inverse of a relation switches the x and y values. That's probably the easiest way to think about it. What that really means is that it undoes the actions of a function or relation. And so if you have a function which when you input 2, you get a 3. And so let's do the stop share. So if you have a function which when you plug in 2, it gives you 3, the inverse function is going to go the other direction. And so the inverse function we write in this notation, f inverse, and it would take that 3 and give you the 2 out of it. And so it's really just flip-flopping the direction of things. It undoes whatever your original function does. That said, when we're talking about equations, it's really easy to calculate these things. The examples that I have in here, 2x minus 3, x squared plus 1, 2 to the x, we should be able to do those. And so let's write them out and then let's find the inverse. And so the first one is f of x equals 2x minus 3. The second one is g of x is equal to x squared plus 1. And the third one is h of x equals 2 to the x. Cool. And so let's see if we can figure these out. To calculate the inverse, you have to switch all of the x and y values, and then just solve for y. And so in this case, we would say that our f of x starts out as our y. We replace it with x. So it's x equals 2y minus 3. Now we solve for y. So we can add 3 to both sides. And then we can divide by 2. And this is what we call our inverse function. And so we could say that this is f negative 1 of x. Notice in this case, our inverse is actually a function. That is not always going to be the case. And as an example of that, number 2. So for number 2, g of x equals x squared plus 1. To find the inverse, again, we are going to switch our x and y values. As I write down the y instead of the x. So x equals y squared plus 1. And so x equals y squared plus 1. In order to figure this out, all we would have to do is move the 1 over. So we'll get x minus 1 equals y squared. And then we square root both sides. But remember, when you square root both sides, you get a plus or minus out of it. And this then is our inverse. This notation isn't the best because this kind of implies that it's a function. But plus or minus the square root of x minus 1 is very much not a function. For our last one, h of x equals 2 to the x. Well, we can replace that by making it x equals 2 to the y. And then we have multiple approaches. Probably the easiest one is to remember how logarithms work, because this currently is written in exponential form. If we wanted to, we could rewrite this in logarithmic form, which would give us the log base 2 of x equals y. And so that tells us that our inverse function is the log base 2 of x. If you didn't recognize that, another approach would be to actually just take the natural log of both sides. And so natural log of x is equal to y times the natural log of 2. And then dividing by the natural log of 2, you get y is equal to the natural log of x divided by the natural log of 2. This is another way of writing our inverse function. And some of you might be saying, hey, wait, those two answers are different. Well, I got bad news for you. These two answers are the same. This is actually a way of showing the change of base formula. We actually just proved the change of base formula. Log base 2 of x is the same as the natural log of x divided by the natural log of 2. It turns out you could use any log base here and you'd be able to convert between the two. And so this is kind of a nice little thing to have here. We can graph these functions, and when we graph them, it turns out they're going to be reflections of one another. Note that the inverse graphs mirror across the line y equals x. We can demonstrate that really quick. Looking at let's do the g of x function. So g of x equals x squared plus 1. That's what the graph looks like. For our inverse, we ended up getting two things. We got y equals the positive square root of x minus 1. And we get y equals the negative square root of x minus 1. Notice that this black graph up here, and if we change this color, this red graph down here, they are a reflection across the line y equals x. And that is always going to be the case with these inverse functions. With our second function, which was, or our third function, which was h of x equals 2 to the x. Well, the solutions we got were y equals log base 2, losing my voice there, of x. And notice that again, it's a mirror reflection. And so that's one way you can verify if something is an inverse. Another thing we're interested in is we're interested in knowing if the inverse function is actually a function. And that's what the idea of a one-to-one function is. And so a one-to-one function is a function which has the property that every element in the range comes from exactly one element in the domain. This is kind of like the function definition, but flipped. And so this is basically saying that instead of passing a vertical line test, a one-to-one function passes a horizontal line test. And so you can't draw a horizontal line without it crossing 2 or more points. If it does cross 2 or more points, then it is not one-to-one. If a function is one-to-one, then the inverse is also a function. And we denote it with the f-1 notation. We do have the horizontal line test, which can be used to determine that. And so when we think of our g of x function that we were talking about, it was a parabola. And so x squared plus 1, this is a parabola. It fails the horizontal line test because if we just did y equals 5, that's going to be going through 2 different points on the graph. And that's why the inverse was not a function. The inverse failed the vertical line test. We won't deal too much with one-to-one functions, but it is important to know about them. Let's see. Oh, this actually asks us to graph them, and then this is asking us to find the inverses. Well, we already found the inverses of these functions, so we are good with that. And so to find the inverse of functions, replace all the x and y values, and then solve for y. And we already did the f of x, the g of x, and the I of x function. The h of x function, very similar. I wouldn't stress it too much. The next subject we have is an introduction to logarithms. And again, I don't really want to spend too much time on it because this is Algebra 2. You all should already feel comfortable with the idea of logarithms. How comfortable? Well, that's a whole nother bag of worms. But let's make sure that we know the fundamentals. I want to make sure you know what the graph of a logarithm looks like. And so let's pull up our good friend Desmos. We know what the graph of y equals e to the x looks like. Well, the inverse of y equals e to the x would be y equals the natural log of x. We also have the log base 2, which we already saw. Log base 2 of x. And no matter what the logarithm is, it's always going to have the same general characteristics. And so notice that much like the e to the x function, this has an asymptote. But instead of the asymptote being y equals x or y equals 0, the asymptote is going to be x equals 0. And so this is going to be going down here, and it's going to go down to infinity very, very, very fast. It's then going to go out, and it turns out the range of this does go all of the way out to infinity, but this is one of the slowest functions out there. And so if we wanted to see how long it would take, well, let's just take our x-axis and stretch it out for a bit. And so let's see if I can go here. And so here it is out to 1,000. And now let's just let it go. And so by the time we're around 10 to the 75th, our logarithm's finally going to hit around 250. And 10 to the 75th, that is a monumental number. For our log base, and that was for our log base too. For our natural log, it's going to take much, much longer. And so it hits 250 way up here at 10 to the 108th. At that point, we're talking about number of atoms in the universe type of thing. And here's the thing, there are other logs. Another common log, known as the common log, is the log base 10 of x. And notice with that one, it's still not even close. By the time we're here, our log base 10 is, let's see, this is at 108 by the time we are at 10 to the 108. And so, well, of course it is. That's a silly thing to say. Yes, because that's how log base 10 actually works. And so it is going at a ridiculously slow pace. And that's the way these logarithms work. Logarithms go slower than any function out there. If you want, you can make these things go slower though, by doing a natural log of a natural log. Natural log of a natural log, now we're at 10 to the 108th, and we're currently at 5. And so this is going ridiculously slow. It will still eventually go all the way up to infinity, but it goes at such a slow pace that it will take just about forever to get there. And we could go slower too if we wanted to. What if we did another natural log there? Well, again, now it's only at 1.7. Eventually, this will go off to infinity, but it goes at such a slow pace. And probably when we look down here, it even takes a while for it to get up to 0. And so, yeah, it takes 15 units just to get to 0. Very, very slow function. And so when you want something to go very, very fast, use an exponential function. If you want something to go extremely slow, use a logarithm. But we can go back and forth between logarithmic form and exponential form, basically using this definition here. And so y equals log base b of x means the same as x equals b to the y. And so when we see something like 2 to the 4th equals 16, let's stop the share real quick. We could rewrite this by saying the log base 2 of 16 is equal to 4. Basically, 2 to the 4th is 16. Now this one's kind of a weird one because 2 to the 4th and 4 to the 2nd are the same thing. And so here's another example. Let's say that we have the log base 3 of 81. Well, what this is saying is 3 to the what power is 81? And in this case, it would be 3 to the 4th power. So 3 to the 4th power is 81. And so we could write it like this, or we could write it like this. 3 to the 4th equals 81. They mean the same thing. The reason we have these two different formats for it, though, is because sometimes we're solving for one variable and sometimes we're solving for another. And so let's suppose that we have something like this. How about 5 to the y is equal to 117? What is the y value? Well, in this case, it's not going to be a nice number. There is no nice value of y that's going to make it so that 5 to the y is equal to 117. It's going to be close to 3, but a little bit less than 3. In order to write this in logarithmic notation, what we can do is we can rewrite this by saying the log base 5 of 117 is equal to y. And this is the exact solution for what y is. Now the only question is, what is the log base 5 of 117? And it used to be that you could use books, which actually listed out all of the different log bases up to a certain point. Or they had slide rules, which could also do it. These days we have calculators which can do it. And I typically use the TI 30XIIS, which does not have the ability to do different bases. And so what we do is we use the change of base formula, which we already showed before. We can rewrite this as the natural log of 117 over the natural log of 5. And that we can plug into our calculator and get an approximation for it at the very least. Natural log of 117 over natural log of 5 should be close to 3. And I get that this is roughly 2.9589. But it does go on and on forever and ever, and it never repeats. It's an irrational number. And so that's the benefit of the logarithmic notation. It gives us a way of actually calculating out this y value. share screen. And we have a number of properties. We've already graphed some things. We can go back and forth between these. We have all of these different properties. And again, it's algebra 2. I'm not going to waste too much time on it. But if you have log base b of 1, where this is any base, it's always going to be 0. The reason b to the 0 is 1. Same here. Log base b of b is always 1. Here, if you have b to the log base b, or if you have the log base b of b to the x, you get x out of it. The reason for that is this is an exponential and a logarithm. And when you take when you do a composition of a function with its inverse, you always just get x out of it. Basically, these two functions cancel each other out. We then have these 3 ways of expanding logarithms or contracting them if we want to. We can get this log base b of xy to be expanded to log base b of x plus log base b of y. Or we can take the quotient of them and make it a subtract. We also have this one where we can actually bring exponents down to the front of a logarithm. We'll use that property a couple of times this semester. Then there's our change of base formula, which we have already used multiple times. Log base a of x is equal to log base b of x over log base b of a, which really I usually go to natural log because natural log is kind of natural. It's the log base e. And if you want, I have a ton of problems. I don't really plan on doing all of these because these are actually problems which I copied and pasted from my Algebra 2 course. And so some of these should be fairly painless. Some of them are a little tricky, but they're not that bad. You should be able to do all of these without any trouble. Looking at them, all of these you should be able to do by hand. All of these you should be able to do by hand. Once you get to these, you're going to need a calculator to start doing them. But they're worth doing them. I mean, there's nothing really that exciting about them. Same with this, expanding, all you're doing when you're expanding logarithms is you're just using these properties. So log base b of xy is log base b of x plus log base b of y. And so that means log base 2 of 5x is log base 2 of 5 plus log base 2 of x. Log base 7 of y cubed is the same as 3 log base 7 of y. Nothing fancy. This one, it's a little bit more complicated. You could bring the 1/4 down, then you could separate it all out into the sum of 3 different things, and then just bring those new exponents down. These get a little bit more interesting, solving equations. Let's try one of these. Nothing else, I'd like to try one. And the one that looks fun would be this one right here. And so let's try that one. Log base 4 of x minus 2 minus log base 4 of x plus 1 is equal to 1. That one looks like an interesting problem. And so when we do this problem, what I would recommend is trying to condense everything first. Because if we can condense this into a single logarithm, then we can use the definition of logarithms to rewrite this in exponential form. And once it's in exponential form, it should solve itself fairly quickly. And so let's start by condensing. This is a subtraction. So that means we can rewrite this, and I'll go with the orange pen today, as a log base 4 of x minus 2 over x plus 1. And I know it goes without saying, but if you want to, you can always pause the video and try on your own first. From here, it's written as a logarithm. And so this is log base 4 of this stuff equals 1. Using the definitions of logarithms, we can rewrite this as 4 to the 1 equals x minus 2 over x plus 1. Well, 4 to the 1 is just 4. And now we can cross multiply, giving us a 4 times x plus 1. We can distribute. We can move terms around. 4 over here gives a minus 6. And then we can divide, giving an x equal to negative 2. And I'm just going to double check that we did all of that math correctly before we do another check. And so what we did was we started with this. We combined our logarithm to give us the 4 there. And so it's going to be 4 to the 1 equals x minus 2 over x plus 1. And then we distributed after we cross multiplied, giving us a 4x plus 4 equals x minus 2. And then we brought the x over, we brought the 4 over, giving us a 3x equals negative 6. And then we get our answer of x minus 2. Good, we did all of that correct. Now here's the thing. That is not going to actually work in the context of the problem. Because when we go to plug this x minus 2 back in to check our answer, we would get log base 4 of negative 4 minus log base 4 of negative 1 equals 1. And I got some bad news. This does not work. It does not exist. Because remember, with logarithms, the domain starts at 0 and goes to infinity. We're not allowed to plug negative numbers into logarithms. And so this solution we got is actually not a working solution. In this case, there is no solution. Which is always fun. You're going to see stuff like that happen a lot this semester, where you'll go through a problem, work through all of the algebra, only in the end to recognize that there's no solution. Now, here's the thing. If you didn't understand how logarithms work, you might have called it a day at that x equals negative 2 and been like, oh, the answer is negative 2. But you have to remember what the domain of these functions are. If you get a solution which is outside of the domain, that's not good. And so in that case, you're going to have no solution. So always keep an eye out for stuff like that. That's why I wanted to do that problem by the by, because it's one of those weird ones where there's no solution. And watch, I made a mistake somewhere and there's actually a solution. But yeah, that's what to expect with these types of problems. We're probably not going to see problems like this throughout the semester because we're not really going to be solving equations for the most part. Instead, what we're going to be dealing with is we're going to be dealing with the function itself. And so we need to make sure that we understand how logarithms work. We need to understand the structure of a natural log, because we're going to be dealing with functions like this, y equals sine of the natural log of x. We're going to have to know what that does. And look at this graph. This is the graph of sine of the natural log of x. Would you be able to recognize the behavior and what the long-term behavior is going to be? Well, that's something we're going to have to be comfortable with. How about the natural log of sine of x? That'll be weird because it should have a ton of asymptotes. There we go. Another thing to note about natural log, sometimes we'll be seeing the natural log of the absolute value of x. And this one pops up a lot, particularly once we get to antiderivatives, which I think is chapter 5. The reason for this is because the absolute value of x basically doubles the domain. If we were to just do the natural log of x, notice that it's only going to be the positive section. But as soon as we make it the natural log of absolute value of x, we get that it's going in the negative direction too. If we had actually had the absolute values in our problem, this probably would have worked out. But because there weren't the absolute values, we just ended up with no solution. Oh, and here's talking more about some of the basics. And so the common logarithm, I almost never use the common logarithm. You see the common logarithm used a lot in science, though, because it basically reduces things down to what the exponent is. And so many things measured in science use a log base 10 because it shows when something is 10 times as large. The Richter scale, which is how you measure earthquakes, typically uses the base of 10, though I feel like that might have changed over the last 50 years or so. Originally, it was a base 10. So a 7.0 would be 10 times that of a 6.0, and so on all the way up. The natural logarithm is the one that I almost always use because it uses the number e. And like I mentioned, e is a very unique number. It's the natural number. It really is. It is the number which comes from nature. When you're talking about exponential growth and decay, it's really all about e and how things are related to e. And so you'll see me almost always go to the natural log over any other logarithm. There's also some applications. I mean, this is a silly one. I think you'll see it pop up in the homework. The pH scale is a measure of how acidic a solution is and is given by this formula. And so the pH is equal to negative logarithm of H plus, where H plus is the concentration of the hydrogen ion in moles per liter. For those of you who have done chemistry, you should understand that perfectly. For me, it's been a while since I've done chemistry, so usually I defer to our chemists. Water has a pH of 7, and then you can make things more acidic by giving it a lower pH value, and you can make it more basic by making it have a higher pH value. These two questions are just asking you to figure out the concentration of hydrogen in Gatorade or what is the pH of milk. And really all you're doing is you're just plugging these into the formula. If Gatorade has a pH level of 2.7, you plug the 2.7 in for the pH, and then you can figure out what the concentration of H plus is. If we know the concentration of hydrogen is 1.88 times 10 to the negative 7 moles per liter, we can take that and plug that in here, and then we can solve for the pH. And so I'll let you guys play with that one if you want to. We also have the idea of exponential growth and decay, and notice this is more of just a big picture idea. Yeah, this is definitely leading into the chapter 3 idea. And so when you think about things in biology and medicine, almost all of it is tied to sines and cosines, linear models, and exponential models. And there's a reason for that. There's a mathematical reason for why those three are the go-to. Your sines and cosines are your oscillations. Your linear is how you're increasing. And then your exponential models are when you are going unbounded. Turns out just about everything can be modeled using those three types of formulas. And we'll see why later on. For now, though, we just want to make sure that we can actually calculate some things, some basic things. And this is models using unrestricted growth. Eventually, we'll have restricted growth, but for now, we'll stick with unrestricted. And so suppose you start with 500 bacteria times t equals 0, and every 1 unit of time, each bacteria will split into 2. Then at time t equals 1, you have 1,000 bacteria. Time t equals 2, you have 2,000 bacteria. T equals 3, you have 4,000 bacteria. And this can be modeled using this formula, 500 times 2 to the t. As budding biological and medical researchers, your goal typically will be to take the data, and so in this case, the t equals 1, t equals 2, and t equals 3, and to create the model for it, the 500 times 2 to the t. And after you've done that, then you can start figuring out all of the underlying principles of those things. And so here's an example. The population of the US was 282.2 million people in the year 2000. And by the year 2010, the population of the US had increased to 309.3 million. Assuming an exponential model, which for obvious reasons, it's not going to be a perfect exponential model, what would you expect the population of the US to be in 2050? What will the model predict, or when will the population be 1 billion people? And so let's try this one. And so in the year 2000, we have 282.2 million. And then in the year 2010, our population is 309.3. And so then the question is, in year 2050, what is the population? And then when will the population be 1 billion, which would be 1,000 million? And we're assuming an exponential model. And so let's see if we can develop an exponential model for this. Perhaps the simplest exponential model for this would be one which is comparing population to time. And so we could say P of t is equal to A times B to the t. There are multiple different formats that you'll see our exponential model take. Oftentimes you'll see things that look like this. Your population is equal to P naught e to the RT. This is another great one. And so you can use that one if you want to. I almost always start with this one because I just like the simplicity of it. And so when we look at this, we have all of these values. We need to figure out what all of the different units are going to be and how we can input things. And so let's start by taking these years. I personally don't like using the year as 2000 and plugging that into a formula. And so instead, let's make it so that year 2000 is actually considered year 0. And so we'll have our time, t, and we'll have our population, p. At time t equals 0, our population is 282.2. At time t equals 10, our population is 309.3. Using these two pieces of data, we can actually take this model and figure out what A and B are. And that's the strategy we're going to take. And so let's start by plugging in that first piece of data. 282.2 is our population. And we're saying that that's equal to A times B to the 0. Well, B to the 0 is just 1. And so that leaves us with A is equal to 282.2. And so already we figured out that one. To figure out B, it's going to be just plugging in the other one. And since we already know what A is, it shouldn't be that bad. The algebra, though, should be very gross. So let's see how bad the algebra gets. And so for the second one, it is 309.3 is equal to 282.2, which we already know our A value is, times B to the 10th. To solve for B, we need to divide both sides by 282.2. And then we have to take the 10th root of it. And so we get B is equal to the 10th root of 309.3 over 282.2. And we could plug it into a calculator and get a decimal for it. No, I probably wouldn't, because the number is going to have so many rounding issues. The only thing I might do is I might get rid of those decimals. Yeah. And so this is our B value. This is our A value. And now we can answer our questions. And so in 2050, we're going to be talking about the year being 50. And so we can actually plug 50 into our new formula. Our new formula being P of T is equal to 282.2 times B, which is the 10th root of 3093 over 2822, to the T. So P of 50 is going to be 282.2 times the 10th root, 3093 over 2822 to the 50th. And now we can plug it in and get a good approximation. And so 282.2 times the 10th root, and I want to do the x root, so 10th root of 3093 divided by 2822 to the 50th power. Make sure I got all parentheses right. That looks right. And I get 446.3459. Yeah, we can round that to 446.3. Now we've got one more. And so our last one, and so we just figured out that the population in 2050, we would expect to be 446.3 million. And so the other one is to calculate when it's going to be equal to 1,000 million, which is a billion. So to figure out when it's going to be at a billion, really it's going to be the same process, a little bit grosser. Because now we're going to be starting with the, what's it called? We're going to start with 1,000 over on the left. Equals 282.2 10th root of 3093 over 2822 to the T. To solve for T, we're going to need logarithms. And so we can start by dividing by the 282.2. But now to get that T down, we're going to need to take the natural log. So natural log of 1,000 over 282.2 equals T times the natural log of the 10th root of 3093 over 2822. And then to get T alone, we have to divide. So T is equal to the natural log of 1,000 over 282.2 divided by the natural log of the 10th root of 3093 over 2822. And now we plug it into our calculator and hope for the best. natural log of 1,000 over 282.2 divided by the natural log of the 10th root. So I'm going to use the x root of parenthesis 3093 divided by 2822. Do a parenthesis to close that. And I think that might be all the parentheses I need. There we go. Oh, I feel like I need another one. Yeah, one more parenthesis. And I get 137.97. Coming over here, if we round that, that tells us that we are going to be getting it in the year 2138. And so if the US population is increasing at an exponential rate, then we would expect the population in the year 2138 to reach 1 billion people. That said, population is not strictly exponential, so we don't have to worry about that. But that's definitely the type of modeling we're going to be seeing pop up a lot in this course. The next one, similar, just going the other direction. So half-life of an object is the amount that it takes for it to decrease to half of its original size. You can do the exact same mathematics to get all of those things done. Instead of doing that, let's go on to sequences. And so a sequence can be thought of as a list of numbers that has some defined order. And so you have a first element, a second element, a third element, a fourth element, and so on and so forth. Oftentimes you'll be given some expression for it. And so in this case, a sub n, I'll write it down, is equal to -1 to the n times n over n plus 1. And then it says, find the first 5 terms in the sequence. Well, we could start with a naught if we wanted to. And so a sub 0, is equal to -1 to the 0 times 0 over 0 plus 1. Well, that's going to give us 0 on the top and 1 on the bottom, which is just 0. A sub 1 would be -1 to the 1 times 1 over 1 plus 1, which is, well, 1 or -1 over 2. A sub 3 is -1 squared. Or sorry, a sub 2, we skipped one, is going to be -1 squared times 2 over 2 plus 1, which is going to be equal to 2/3. A sub 3 is -1 cubed times 3 over 3 plus 1, which gives us a -3/4. And at this point, you should be able to see what the pattern is. And so we could write it like this, one element at a time, or we could actually just write the set. And so the set, in this case, would start with 0, then -1/2, then 2/3, then -3/4. Then it would be a 4/5 and a -5/6 and a 6/7, and you get the idea. And so this is an algebraic way of writing out this sequence. That's really the big idea behind sequences. Sometimes you're going to be starting from this side and going towards the list. Other times you're going to be starting with a set like this or a sequence like this and be asked to figure out what the formula is. Let's take a look at number 1 here. The second one is a little bit harder. So let's try that first one, just so that we can get the idea of it. So if we have the set -1, 4, -9, 16, -25, and on and on. Well, in this case, let's say that we want to start with n equals 1. And so this would be saying that a sub 1 is equal to -1, a sub 2 is equal to 4, and so on. The question is, what pattern do we have going on here? And hopefully you can all recognize that this is a squaring pattern. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And so we could say that a sub n is equal to n squared. And that'll get us the number part. But in order to figure out the sign, notice it goes negative, positive, negative, positive. We saw that behavior on that last problem. And that comes from something like this. Whenever n is an even number, this goes positive. Whenever n is an odd number, this goes negative. And so this would be the way of writing out this sequence. Another way we could do this is if we wanted to start with this being a0. A0 equals -1, a1 equals 4, and so on. We could do the same process, but we'd have to shift everything over by 1, because for 0, this is 1 squared. At 1, this is 2 squared. And so for a sub n, it's going to be equal to whatever the n value is plus 1 squared. And then to figure out the sign, well, -1 to the n would make it so that at 0, we would be getting a positive. And so we would need to adjust that just by adding 1 up here as well. Now you could actually check it out. And so at n equals 0, we get a sub 0 is equal to 0 plus 1 squared times -1 to the 1, which it turns out is -1. It's always a good idea to check your answers. And so in this case, you could go with this answer. You could go with this answer. Really, you'd want to check to see if it's talking about utilizing an A0 and A0, or if it's starting the sequence at A1. And hopefully the directions for homework and whatnot will actually say that. Yeah, depending on what type of stuff you're doing, you might want to start with A1, or you might want to start with A0. And so it really does depend on what you're doing. All right, next up, we have the idea of recursive sequences. Recursive sequences are a little different. And so instead of having a nice formula, recursive sequences are actually tied to prior data. And so previous elements. And I've got a couple of examples here. The first one is actually dealing with starting with 2 values. And so let's say that a sub 1 is equal to 1. A sub 2 is equal to 3. And then our recursive formula is a sub n is equal to a sub n minus 2 plus a sub n minus 1. Let's stop the share and take a look at this. And so if you have something like this, to figure out what A3 is, we can use this formula. A3 would be equal to A1 plus A2. Well, A1 plus A2 gives 4. to figure out a sub 4, that's going to be a sub 4 is equal to a sub 2 plus a sub 3. 3 plus 4 is 7. A sub 5. You might notice the pattern at this point. It's just adding the prior two elements. So 4 plus 7 is going to be 11. A sub 6, well, that's going to be 7 and 11 is 18, and so on. I believe these are called Lucas numbers. I think that's the name of them. You should double check. They're very similar to Fibonacci sequence. The Fibonacci sequence is basically this, but instead of starting with 1 and 3, you start with 1 and 1. And so that's the core difference there. But that's how recursive sequences work. And you see them a lot in biology and medicine. We'll actually be doing a few problems, which will just keep going throughout the entire semester. Another example I have on here is a sub 1 equals 2. So let me write this one down. So a sub 1 equals 2, and then a sub n is equal to a sub n minus 1, and then it is minus 1. No, it's 2a sub n minus 1, minus 1. There we go. And so in this case, instead of having two different values that we're comparing, we're only going to be using one. And so a sub 2 is going to be equal to 2 times the prior element minus 1. And so 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5. 2 times 5 is 10, minus 1 is 9. 2 times 9 is 18, minus 1 is 17. And we could ask for patterns related to this sequence, and there's a number of interesting patterns related to this sequence. It might even be worth exploring them. The next one would be 33, and so on. And so that's what a recursive sequence is. A recursive sequence is a sequence where the next element is tied to the prior elements. Recursive sequences like these are also called difference equations. First order difference equation is one which new values just come from the previous element. So it'd be that second example. A second order difference equation requires two prior elements. I'm guessing you can guess what a third order difference equation and a 17th level or 17th order difference equation would look like. And so hopefully you can figure that out. Here's a couple of special ones. Logistical difference equation and then the Fibonacci sequence. We'll see logistic growth a lot this semester. And if you're taking 356, even more there, because it's all differential equations, and that's a big part of that course. But the last thing I have on here is this problem right here. And so bacteria often grow on agar plates and form circular colonies. The area of the colony is proportional to the number of bacteria it contains. The agar, which hopefully you know what agar is a resource the bacteria uses to produce, and so only those bacteria on the edge of the colony can produce new offspring. Therefore, population changes according to the equation n sub t plus 1 equals n sub t plus I, where I is the input of the new individuals and is proportional to the circumference of the colony with the proportionality constant R, i.e. I is equal to R times C. So R is the radius, is that right? Yeah, something like that. No, that's not. Derive the recursive formula for population size n sub t plus 1 as a function of n sub t. And if you want, I've got it worked out here. This one actually came straight from your textbook though, and so you might want to go and look it up in your textbook to figure out how all of this came to be. Basically, n sub t plus 1 is equal to n sub t plus I, we know that I is equal to R times 2 pi R, where R is that proportionality constant, not the radius, sorry about that. And then pi R squared is equal to K times NT, where K was given up here as the proportionality constant. And then we can just solve for things and plug them in. And so if we know that R is equal to the square root of KNT over pi, which comes from this formula here, then we can plug that in here to figure out what I is, and then we can plug that into this formula. That one is harder than what I would typically put on a test or anything like that, but it's one that's worth seeing because this is one of the first real applications which you can see related to this stuff. The applications typically aren't going to come into full effect until we get our derivatives. Once we have our derivatives, the universe is nothing but derivatives. And so we're going to be seeing a lot of bio and medicine applications at that point. For now, we're just learning the basics. And we're not even learning it because, again, this is all review. And that brings us to the end of today's lesson. And so we covered exponential functions, logarithms, and sequences and difference equations. There might have been a few new things for you. I don't know how much you did with sequences and difference equations in Algebra 2, but everything else should have been fairly familiar. You should know exponentials and logarithms like the back of your hand. But if not, well, it's definitely time to brush up on stuff. And so remember, you have a ton of homework. Get that homework done, and I'll see you in the next lecture.